Okay, here we are, week 1 distance learning, and we are looking at the Ohm's Law PhET, which you should have had a chance to look at already. So this first portion here, I'm not going to do for you. You're just basically playing around with the simulated lab, right? You can either Google that or I had the link on Canvas. But basically the point you were supposed to get across was this relationship right here. Right? Looking at the relationship between resistance, right? And the unit for resistance would be the ohm. We're also looking at current, which has a unit of the amp. And then we are looking at voltage. All right, voltage having the unit of the volt. All right, the relationship we should have seen was that resistance, right, is what opposes the flow of current. So if you are increasing your resistance, right, you will then have a decrease in your current. Or if you want to keep the same current, then you would have to have a greater voltage to make up for that increase in resistance. All right, so that's the relationship that they were really looking for question 1 there. To look for the mathematical relationship, they gave you some numbers there, right? And if you were just kind of to plug this into a calculator, play around with it, you would have pretty quickly seen that the voltage would be equal to the current times the resistance. All right, that is a super important formula. All right, that one is called Ohm's Law, saying that the voltage is equal to current times resistance. If we want the current to be as large as possible, right, that would be I. So you would have your voltage be as large as possible and your resistance be as low as possible, which kind of makes sense, just, common sense wise. If we were going to use a metaphor here, we can think of voltage kind of like water pressure, right? So if you were to try to increase the flow of water through a pipe, you would want to increase your water pressure as high as possible, right? And then you would decrease your resistance. So, as large a hose as you could possibly get with no turns or kinks or anything along those lines. All right, for this part here, right, we're supposed to determine the direction of electron flow. So in the simulated lab, they gave you the direction of the conventional current. Right, and because when they determined the direction for conventional current, they didn't actually know anything about electrons, this is actually backwards to what's happening in real life. So even though we define conventional current as what a positive charge would do, electron flow is actually the reverse of that. So electrons are actually flowing in this direction. So if we wanted to figure out which terminal was which, right, with our conventional current, if we assume that to be a positive charge, they would be leaving the positive side, right? Positives repelling positives and being attracted to the negative side over here. If you look at actual electron flow, it's the same thing. The negative electrons would be repelled by the negative side of the battery, and they would then be attracted to the positive side of the battery over here. So my pink is actual electron flow. Right, annoying, but people have been doing that for hundreds of years, so it's not going to change now. Table, again, I didn't do for you. You just go through and plug these numbers in. It's a little bit hard to get these exact voltages. As long as you're pretty close, it's fine. And you would end up with a graph something along these lines, where my purple is the 800 ohm resistance, my red is the 405 ohm resistance, and the orange is my 40 ohm resistance. You can tell the big difference there is obviously their slope. And we would then want to figure out what the physical meaning of that slope is. If we find the slope, that is obviously rise over run. All right, and in this case, what is our rise? Our rise is our voltage. That's what we graphed on our y-axis. And our run is our current, which we graphed on our x-axis. If we were to go back to Ohm's law, V equals IR, right? Well, we have voltage right there, and we have current right there. So if we solve Ohm's law for resistance, we get voltage over current. Voltage over current is our slope. So the physical meaning of that slope is the resistance. All right, so you can see here that our 40 ohm resistor had a nice shallow slope, a slope of 40. While our 800 ohm resistor had a really steep slope, and that slope would be 800 if you were to solve it out. Last but not least, is it possible to decrease the resistance of wire without changing the material? Obviously, material matters, right? That's the whole reason that we use copper for our wire, because it has a pretty low resistance. We don't use silicone or rubber or anything along those lines. But other things that can decrease resistance would be things like length. Right, the longer your wire, the more resistance you're going to have there. Right, so if you have power lines, things along those lines, you have to make those thicker to make up for the length. And the thickness also makes a big difference. Going back to our metaphor of water pipes, if you have a really thin pipe, then you're going to have a lot more resistance than if you have a much larger one. All right, and that is our PhET simulation. Hopefully you guys are having a nice break, and make sure that you're emailing me if you have any questions.